Am I audible yet? Just checking. Well, hello there, everyone. Let's get right back into the stream. Last time, we were just starting to set up buffers for rendering anything to the screen. This time, we will continue right from that particular part. So here in the mist data, we had just added vertex buffer and vertex buffer allocation. So each buffer requires an allocation associated with it. Normally, you will do it with VK allocate memory. I still don't remember what the actual name for that was. But now we will actually start using, we just will start using VMA because I'm not trying to learn here. I'm trying to directly use things, and VMA makes it that instead of having independent, separate allocations every single time, you make one large allocation and then split out parts of it for different buffers. This is better to go around with memory allocation than usage for GPUs. NVIDIA explicitly recommends using this kind of methods on their Vulkan do's and don'ts. So we'll continue from here, right? We have a vertex buffer and vertex buffer allocation. We haven't yet created them. So let's go to the init and check them out. Here we have done it after pipelines. So after pipeline is created, that's there, I believe, shader module. But that's the pipeline. No, that's the dependencies. So this is the pipeline creation. This is the barrier creation. We'll just comment it out. Barrier creation and pipeline creation is here. Right. Pipeline creation. Okay. So just close that. Barrier creation requires its own braces. So I'll add that. It will work out eventually. So long as it's correct. Build solution. Looks just fine. Okay. So once pipeline has been created, we want to create buffers. So vertex buffer creation. And here we want to allocate, we want to create buffer. First of all, we'll do it using VMA directly. So VMA create buffer. You have an allocator requirement, that is the VMA allocator. So that comes from device, render device, or GPU allocator. Buffer create info, we'll make that. Create info, allocation create info. That is a second thing. So actually we do need that too. Allocation create info. P buffer, so that is the that's the vertex buffer that we have. Allocation, that's the vertex buffer allocation that we have. And allocation info. So that's optional, as you can see here. Can get some other information. We will take it anyway. So allocation info. And all of this will be under VK check because this can fail. Okay. Let's get to creating each of these. First is buffer create info. So VK buffer create info there. First buffer create info. And we'll designate it initialize there. VK structure type buffer create info there. P next is null pointer. We don't have any additional things that we want. Flags is 0 here. Size for the buffer. So what size do we need? I will just put 2 for now and we'll come back to it in a second. Usage, VK buffer, usage, vertex buffer bit. This will tell the system that this is a vertex buffer. Okay. Sharing mode is VK sharing mode exclusive because we don't want to share it between queues. It will always be on our main direct queue. Queue family index count will be the direct queue index count. So in the device.direct queue family index. All of this will soon be moved out. We will stop using the direct objects and we'll start using getters and setters. But for now, we're fine with this. Q family indices. Oh, wait, sorry. Q family index count is 0. Q family index is null pointed. Because we're not doing sharing. I forgot about this, but effectively, if you look for it, buffer create info, index on the number of this thing, it is ignored if sharing mode is not concurrent. So it will be ignored. We don't care and we don't have to keep it. All right. So that is buffer create info. We also need VMA allocation create info there. Const allocation create info. Right. And designated initialize. Flags is 0 for now. VMA, we can check what the flags are. Allocation create flag. Okay. Here's the thing. We can have all of these. So let's look at it. Dedicated memory is useful if something needs its own allocation. We don't want this to have its own allocation. We have multiple different buffers sharing this allocation. That is good for us. Okay. We want to have a mapped bit. This will map it to the CPU. We want to have VMA allocation create. I'm just looking through it, but most of the time we want host access sequential write bit. Okay. So what does that allow us? That allows us to directly write from the host. VMA memory usage auto. It will decide whatever we need. It's better at it than us anyway. Required flags. We keep memory properties. We say memory property. Host visible bit, I suppose. Preferred flags. So this will be automatic. What I will do is I'll move this flag into prefer. We prefer if we have a host visible thing, but for vertex buffer, because we only have to write it once, we don't care if it is host visible or not. Memory type bit. VK memory. I don't think this is VK, is it? You can see. You enter your memory type bits. Bit mask for every memory type acceptable. If pool is not null, this member is ignored. VMA pool. That's default pool. Default pool. This will be null PTR. User data, null PTR again. We don't particularly care. Priority 1.0. It is a float, yes. Memory type bits. We leave it to 0, I suppose. Yep, looks good. So that is allocation create info. Finally, we want VMA allocation info itself. We don't want to allocate this manually. This is an output from VMA create info. Okay. There I have a little issue. We did not close this one. Okay. And that should be fine for now. We will just go to the miss data header. So this is the vertex. This is the vertex buffer. How many vertices do we need to make a cube or a triangle? Let's start with a triangle. How many do we need to make a triangle? 3, right? So the size here would be 3 times the vertex size. So we will actually create a U size P vertex buffer size, and hold on, I want to try something. Maybe interesting. There's a small change, small difference between how Visual Studio is formatting things and how ReSharper is formatting things. Hello there. Okay, so size here will be vertex buffer size. Did we not create it? List data.h vertex buffer size is right here in list data. So here it should be valid. Date is valid. We do need to compute it though. So vertex buffer size equals size of vertex multiplied by 3 vertices that we need. What am I creating? I'm creating a renderer in Vulkan. Okay. It's close export, why not? Yes. Right now we start with 2D and then we take it to 3D as a step by step. So we just have a triangle running and we're just working on adding it using a vertex buffer. Once that is done, we'll add a camera and move things around and so on and so forth, step by step. So this is the side of the vertex buffer. We allocate it here. All of that is done. This should be fine. Okay. Now we need a few more things. One, we need to write to this buffer. And we are going to do this ahead of time. So in missdata.h, I will create the data here. So vertex, vertices, and we'll just hard code that for now. And inside missdata, here we write into it. So vertex vertices is equal to vertex 0 is equal to a vertex. As in initialization, position takes 1.0, comma, 0.5. We can copy it from our style code actually. So copy and paste it here. So that's each of these is one now. We will this. Color is this one. Nothing but red, really. That's vertex 0. I'd like to just initialize this by using an initializer list. Unfortunately, there are no move semantics and everything for the built-in arrays. In fact, I can just use std array here. Might be a better idea. It will support initializer list. Okay. And here we go. So instead of doing vertices one manually, we should be able to now just say vertices equals double array starter, comma. Yes, I do find it quite interesting to do it. Mostly doing it for my own learning. Formatting will rewrite that. It's not happy because we need 3 of these. Now it's fine. Nope. And wait list instead array. Checks out vertex 3. This is a vertex. We need to manually write that each of this is a vertex. unfortunate, but reality. Second one here, third one, third one's here. Similarly, might just be worth it to manually edit the colors. Okay, so with this, we don't need that. The vertices have been allocated. First expression like that. Okay, vertices have been allocated, no problems there. This would go here and allocate allocation info dot. This will give us the mapped data like that. If mapped data, so if it is mapped, we will move it to required actually. That way we don't have to make that assumption. We don't have to check if map data is proper or not. This will be mapped because we did say create map bit, but because we mapped it, it should be fine. Mem copy destination is allocation info dot map data. Source is the vertices dot data. Size is vertices dot size times size of. And instead of doing anything like decal type vertices, I will just do a size of on the element itself. Okay. Now we built. Okay. One more thing. When we destroy, we need to remove any semblance of the device and the other thing. So VMA destroy buffer. First, it takes the allocator. So device GP allocator takes the buffer, which is vertex buffer, the allocation, which is vertex buffer allocation. This should be all take. So take from here, take from there. That will ensure that things are working properly. Build. And well, okay, the triangle is still there. So far, we're fine. We haven't broken anything completely. Vertex buffer has been added, but it's not something we're using yet. In order to make sure that the buffer here and the buffer there are different, we will change this to an isosceles triangle. So red would be at 0.500. And that should be enough to see the difference. Okay. So those are vertexes. We don't particularly care. We don't need comments anymore. Now we need to use this vertex buffer from somewhere in the name. So we go back to the Blaze main thing. Now, during the rendering, so which happens right here, command draw, we will first bind the buffer. So we can bind vertex buffers. Okay, command buffer is CMD. First binding is 0. Binding count is 1 because we only use one buffer. The buffer is misdata dot vertex buffer. It requires an array of size 1. In this case, it's just nothing. And offset should be 0. Okay. We can't give it a null pointer. We need a VK device size offset. And that offset is 0. And then we pass the address of this offset here. Because this can be const, expression, static, offset. Const expression is enough. So this is fine. Vertex buffer. Cool. This will fail. We can open the configurator. There's music in my wallpaper. Hey. Shouldn't be a problem anymore. Anyway, so if we try to run it, it will actually give us a warning saying that vertex, it will not. Interesting. We're binding a vertex buffer, but we're not using it. Nowhere in the pipeline have we said that vertex buffer exists here. So for this matter, we need to add it to the pipeline creation. Let's go pipeline with the shader stages. This is the vertex input state. So these are what we need. Okay. So first, this one is of the type VK vertex input binding description. So VK vertex input binding description. First binding description. So binding stride and input rate. We'll get to that in a second. This won't be constant expression anymore. So what is the binding? Binding is 0. What does that mean? It means that at location 0 in the input, we have this particular thing. Stride. What is stride? The stride is how many steps do we take between, two objects. So stride would be size of vertex, because each object is vertex apart from each other. And this one will be vertex here. We can also give inputs which are at instance level. So each instance has its own input, but in this case, we're not bothered by it. Oh, wait, this can be cost expression. So this can be a cost expression as well later on. We don't particularly need to right now. So binding description has been provided. This will only take one binding. We'll get to that. But VK vertex input attribute description, cost expression, attribute description. So location 0, binding 0, format is size of, no, format is RGB. So VK format R8, R32, G32, S float. So this says there are 4 components. Each of them are 32-bit floats. They're signed floats. Okay. Offset is offset of. This takes S, which is the structure name. In this case, that's vertex. M, which is the particular part of the structure we need, which is the position. Okay. And there are 2 attributes. So this is actually an array. We can just make it std array of attribute description. So equal to, make it braces. Don't need that. That's not a semicolon either. Copy this, paste it here. Happens sometimes. So these are the attributes. Location will be 1 now. Binding is still 0, I think. I haven't used these in a while, so I don't remember exactly what the difference between binding and location was. So then I'll check this. Here input location number, binding number in which this attribute takes its data from. Okay, so vertex binding is 0 here. This is where it takes the data. And this is how it interprets the data. So location 0 will give us vertex. Location 1 will give us color. So this is attribute descriptions dot size dot static cost and attribute descriptions dot data. And that should just work out. Build. Okay, run. Okay, it says that attribute at location 1 and location 0 are not consumed by the vertex shader. So now we go to vertex shader. In the input, instead of just using vertex ID, we will start using vertex position. So that's a float 4 position and float 4 Oh yes, comma there. Color. Let's see how it works in slang, because slang is new to me. Vertex input. Slang documentation. Vertex input. User defined output from one stage are bind by order of declaration. Semantical or identical. The position binding semantic. The uniforms, bindings, entry point attributes or stages. So it uses by order. It should just work. Build solution, let's see. Compile the shader, run it. Cannot execute. Because this is a completely different problem. Sometimes it happens when things aren't linked properly. Okay, it is still not consuming. So here, that's because we haven't changed it here. Position, color. Okay. Build solution. I think I'll have to rebuild this. So otherwise it will give us an error probably. Run it. There we go. We are now using the vertex buffer. We have moved this particular point. You can move it from the CPU as required, as and when required. So let's try that. And this is on the CPU, right? So on the CPU side, on this particular thing here, we can change X to keep it to 0.5. Y, we can move it to 1. So this means it will go all the way up. We run it. And there we go. It touches the sky. We have moved to using vertex buffers. Still, this means we don't have a camera. Okay? We still don't have a camera. We need to add something for that. Just checking. Okay. So how do we get cameras? First, we need a structure, just like vertexes, but we don't provide it using a vertex buffer. We do something else for that called uniforms. And we need to write camera to it and then read from it on the other side. Now, this requires certain libraries. There is DirectX Math or there is GLM. I'm kind of familiar with GLM already, not so much familiar with DirectX Math. But, always up for some experimentations, and let's try out DirectX Math. Oof, this is very bright. Sorry for the flashbang, everyone. Settings, dark, disabled because this fingerprinting is enabled. Shy, oh hey. Oof, okay. Light mode it is. You're gonna have to deal with it, guys. Okay. So let's use DirectX Math. First thing, we need to add it from VC package. So we go here, we say DirectX Math. 1 second. There was some weird noise in my room. I need to check it out. I'll be right back. And I'm back. Sorry for the delay. So DirectX Math, I believe that should be it. Nope. Rebuild solution. No, DirectX Math is not a port. because the code name is different. Vertex math PC PKG. Where is it? Look, let's look at PC PKG. DirectX TK. We don't want that. DirectX math. Okay, there's no line in it. Sorry, no dash inside it. Build solution. It will install DirectX math for us. Cool. One thing, if I'm correct, if I remember correctly, today's stream is about making a box. Okay, it's Vertex buffer. I was initially calling it a box. We should do that. We should add a box. So instead of this, I will make it a box. How many vertexes does a box need? So you might think it needs 8 because there are 8 corners to a box. But because we don't have index buffers right now, indexes are a different thing. We will need 1, 2, 3. So that's first triangle. 4, 5, 6. That's the second triangle. That makes one side. 6 per side. 6 sides. So that is 36 unique points to create this, entire cube. We'll get to it in a bit, I guess. I don't want to write 36 elements at the moment, especially not manually. So DirectX math, build solution, we already did that, I believe. So let's start using it. So inside miscellaneous data, we will have a camera. So what does a camera need? A camera has a few matrices. Here we will include the DirectX math. Okay. We need an XM float 4x4. Okay. So XM float 4x4 is a matrix that is 4 by 4 matrix, the most common type of matrix used. This is the view matrix. And then there is a perspective matrix that we need. Effectively, anything that we see on the rendering, like on the screen, is a set of linear algebra transformations that are happening to our initial vertex. So while we initially drew the triangle in the screen space, which is -1 to 1 on X and -1 to 1 on Y, 0 to 1 on Z, instead of that, now we will use 3-dimensional space that runs in meters or centimeters or something and convert it to the screen space through a set of transformations. So a view matrix is the one that is responsible for converting from the world space to the space of the camera, right? So effectively at the end of a view matrix, the entire world gets fixed in a way so that the camera is at origin. Okay? So instead of, rotating the camera, you actually rotate the world around the camera. And perspective matrix is similar, except instead of working on moving anything, it will shrink things that are farther away from us so that you get a perspective view of the things, of the system. So these have to be created. Okay. Now I'm going to hard code the locations, but I'm also going to write them here. So DirectX XL float 4. So that's the position. So that's a camera position. There's also going to be camera direction. So it can add a direction, which is instead of XM float 4, I think it's an XM. There's no quaternions here. I need to check how to get quaternions. DirectX math quaternions. I know it's a bit weird using DirectX math inside Vulkan, but Vulkan doesn't care. This is just a library we're using. XM quaternions. Quaternion dot function quaternion exponential quaternion equal. It just says an fxm vector. Here, what's an fxm vector? Vector intrinsic. Okay. Interesting. What are these? We, you know what? Let's stick to familiar things. Build a rebuild solution. It will break because we removed DirectX math. Instead, we will have GLM. I do want to learn how to use DirectX math eventually, but right now we can just use the things that are available to us. Okay. It failed, build solution again. GLM.s not found. That's completely fine. GLM slash GLM.hpp. That's the math thing we'll use. So now we can do GLM mat 4x4 view matrix, GLM mat 4x4 projection matrix, GLM vec4 GLM vec4, which is camera position, and the camera target. Let's make it target. Let's not use the quaternions for now. Okay. So what is happening here is we will create these things. We will hard code it temporarily, and then we will send it to the GPU. Once they've been sent to the GPU, we can start making it a bit more manual, where it can be controlled over time. So inside init, this is the Vertex shader. So Vertex, so that's the pipeline first, then it's the Vertex buffer. We don't care about either of these. Camera will be here. So camera. This is why we have the misc data struct. It's literally just miscellaneous data, right? We'll be removing it soon enough, but for now it's fine. So first thing we need to do is create the position. So position equals vec4 GLM net4. Make it 0, 0. Actually, let's make it 2, comma. So make it make it be at 2, 2, 2. Position, have a W coordinate of 1. Camera position, then camera target. Let's make it target the origin. So this will be 0, 0. Scalar, and that's fine. It will automatically, evaluate everything to 0. W equals 0 and W equals 1 is both the same thing if you look at origin itself, because origin is, origin. Actually, it's not. It's not the same thing. So we will make sure it's a homogeneous coordinates. All right. So camera position, camera target, camera. Next is the view matrix equals GLM view. Then let's look at. So look at isn't here. We need to include it. So include GLM slash none of those. Was it common? I don't think so. Oops. No. G2C. What are you making? Same question again. It's a 3D renderer in Vulkan. GLM look at. So where is GLM look at? Stack Overflow, everyone's friend. Necessary quickly only. Who does look at belong to? Look at. So look at is just set the documentation, USB the documentation. It's not the documentation. JLL look at header clip space. Yeah, let's just keep we'll just give it a look once. We do have a look at. So fine. I is camera position, center is camera target, and up is y equals 1 for us. So in this case, it will be GLM vec 4 0.0, y equals 1, 0.0, and 1. It's a direction, so 0.0 here. Okay, what's wrong with this? Fail to match type vec 3 against vec 4. Right, because all of this works with vec 3s. Again, camera target has to be a vec 3. Vec 3. Which makes sense. Homogeneous coordinates are not necessary in the space outside of, your actual rendering thing. But still, this is a bit of a not so nice thing. Projection matrix equals GLM perspective aspect. So FOVY expressed in radians. In the y direction, what is the view that we're looking at? We're looking at 70 degrees. We don't have that here, so GLM radians takes degrees. That's 70.0 f. Then it takes an aspect ratio. So aspect ratio is the width by height. We will hard code it for now, which is 16 by 9. Very common aspect ratio. And the aspect ratio they use is linear. The larger this is, the better for floating point accuracy, worse for rendering. So it's better for Z fighting things, Z resolution. So it's better for rendering. And it's worse because there's only so much fluids you can have, so much precision you can have. So you lose precision on how far you can see. So if we, let's say, can see 1000 meters away, then the Z near being 0.01 might be too close. Sometimes it depends on a lot of other lot of other things. Okay, so we have view matrix and projection matrix here. Both of these have been added. So next step would be to create another buffer. This one will be a uniform buffer. So we go back to miscellaneous data. We had the vertex buffer. Now we create a VK buffer again. VK buffer, uniform. So camera, uniform buffer, VMA allocation, camera, uniform buffer allocation. One of those names can be a little bit of a pain, but it's a necessary thing. Camera buffer. I'm just gonna copy that. Size. Okay. And now we need to assign each of these. So we'll go into init. Go down all the way to where we created the camera stuff in the source camera. We do the vertex buffer, uniform buffer creation here. So first, we can copy most of this buffer create info, allocation info. All of this we can copy directly here. We will have to edit it quickly before we forget. First of all, the usage is no longer vertex buffer. It is a uniform buffer usage. This will be uniform buffer size. Camera uniform buffer size. Everything else is more or less the same. So no problem there. You mapped bit, host access sequential write, those are same. We want it to be just this. No matter what we do, uniform buffers at least, we want to keep host access sequential write bit and mapped bit. That way we can update it often enough because we will need to update uniform buffers. While vertex buffers, we don't need this. But the only reason I'm using it is because I have a GPU and a motherboard that allows me to use resizable bar or SAM, depending on which company you have, right? It's rebar for NVIDIA, SAM for AMD. But at the end of the day, I'm allowed to write to any of the parts of the RAM that I have. I don't need to be in a specific zone. So I don't have to take care of only using important bits in host access. Because host access is normally on non-rebar system, the host visible memory is limited compared to the entire VRAM, right? So if you have 8 gigabytes of VRAM, your host visible will not be 8 gigabytes. But if you have rebar enabled, then host visible will be 8 gigabytes. So, that's the benefit you have there. All right, so buffer create info, allocation create info. Allocation is almost the same allocation. So internally, VMA might actually put both the buffers, vertex buffer and the uniform buffer, on the same allocation. But here things change. Instead of vertex buffer, this is camera uniform buffer. This is camera uniform buffer allocation. Allocation info, this part will remain the same, but this will change, right? So I'll just write to do here. We'll come back to it in a sec. Okay. Now we have created this. We don't have a size yet. So what will be the size of our uniform buffer? What do we want to put on the uniform buffer is a better question. So that will be the view matrix and the projection matrix. Okay. The camera position and the camera target are irrelevant to the GPU. So we don't care about that. So effectively, what we want is uniform. So camera uniform buffer size equals size of the view matrix plus the size of the projection matrix. Okay. That is it. Nothing else. That will automatically do this for us. Map data, mem copy. Here, there will be a little bit of a difference and a little bit more work to do, let's say, because one way is we can directly copy to map data each of the matrices. The other way is to copy first to another location inside memory and then copy to the map data. Or the simplest thing, which is what I will use now, is to create a struct, which is camera data. Put the view matrix and projection matrix in that struct. I'll move the struct up there because coding standards are a thing. Camera data. I will put camera data here, right? Okay. Now the nice things would be one, here I'll have to say camera data dot view matrix, camera data dot projection matrix. But instead of saying size of view matrix and size of projection matrix independently, I can say size of camera data directly. Similarly here, instead of doing this one by one, mem copy, the source would directly be camera data. And the size would be size of camera data, right? Done. The allocation will happen, the copy will happen, everything should be fine. Similarly, in destroy, we want to destroy the uniform buffer. So camera uniform buffer, and camera uniform buffer allocation. Done. So with this, it should just work. Yes, we don't have anything else added to this. It says something has not been destroyed. Device memory. So device memory has not been destroyed. It says we are deallocating things here, which means the problem that exists probably is inside here somewhere. 1 second. Inside destroy, there we go. So VMA destroy allocator. We did not do that. Take GPU allocator, right? Because we did not destroy the allocator, VMA never freed that memory. Okay, that's fine. Things are fine for now. All right. Now, once we have the uniform buffer, this needs to be given to the GPU in some way. That is, inside a shader, we create something known as a uniform buffer. Okay, this is a slang shader, so it uses something known as a parameter block. We will call it camera data structure here. I'll make this call this camera struct camera data. Add the matrices here. So float 4x4 view and float 4x4 proj. I'm not calling it projection, I'm just calling it proj, but that is fine. Okay. Once we have this camera, it's a uniform. We will take out position and vertex color here. Inside position, we will multiply it with the camera dot view. So here there is a small issue that sometimes occurs, which is depending on whether something is a row major or column major, this might actually fail. And we look at that by just tweaking it. Later on, I'll probably read what is needed and correct it myself. So camera.proj and camera.view, these are fine. This is fine. Build solution. Okay. Now if I try to run it, it will give us an error. That one is not the error I was talking about. Rebuild solution. Now if we try to run it, it will give us an error right there because graphics pipeline, it says that it requires a particular descriptor set. This doesn't exist. Okay. So what is a descriptor set? Each of these parameter blocks that we have need to be given to the CPU side of Vulkan through the pipeline creation, right? And this particular signature of having the parameter block is known as a descriptor set. Again, parameter block is non-standard. You have to read up on slang and how it translates to Vulkan itself. This is not an education stream. This is code and all. So I'm not going to dive too deep into descriptor sets here. However, the place where we need to get descriptor sets is in pipeline layout. So we create the pipeline layout here and we will destroy it on the other side. Similarly, we will need to create VK descriptor set layout. And after the uniform buffer, we need to create VK descriptor pool, and VK descriptor set. One of these will be simplified soon enough. We won't be using this in the actual renderer later. But for now, I'm adding this because step by step. So misc data init. So we'll go to the misc data.h, but here inside this init, before I create the pipeline layout, which is right there, pipeline layout create info, you can see that it asks for set layout count and set layouts. So we can create the VK descriptor set layout, create info, announced expression, descriptor set layout create info equals all that. Then VK create descriptor set layout, device, descriptor set layout, create info, null pointer. So the allocators and set layout will be descriptor set layout. Big amounts of things you need to do for Vulkan, all to get the triangle thing, right? VK, structure, type, descriptor, set, layout, create info. Next is null pointer because we don't need anything here. Flags is 0, binding count is 1. P binding is and binding. Okay. Okay. Now we need to create that. So VK, descriptor, set, layout, binding equals whatever is inside the braces, dot, designated initialization. I'm going to first clear that out. So binding is 0. Descriptor type is descriptor type uniform buffer. It's uniform block inline here, but it's actually going to be uniform buffer there. Descriptor count is 1 because you only have one descriptor count. Descriptor stage takes a shader stage. So shader stage vertex bit, which would be fine for us. Immutable samplers is null pointer. Immutable samplers is useful when this is a combined image sampler, because if you have a texture, you want to have an image with it. In this particular case, we don't have that, so we don't care. Const expression, since all of this is const. So this is fine. Goes in here, creates the descriptor set layout, all fine. Since we created the descriptor set layout, we need to destroy the descriptor set layout. We can destroy this descriptor set layout. So like there, device, descriptor set layout, null pointer on the allocation callbacks, right? Take. Seems like I have forgotten take for pipeline layout. And take for pipeline. Cool. That's that. So create and destroy for descriptor set layout is done. What this does is it tells the pipeline that here there will be a descriptor set. Okay. So it says at binding number 0 inside the descriptor set. So here's the descriptor set. Inside the descriptor set, there is one binding. At binding 0, there is a uniform buffer. There is only one of it. So it's not an array. It has a vertex. It's only available in the vertex shader. And that's that. Creates the layout. Layout has to go inside the pipeline. So here 1 and ampersand descriptor set layout. So now the pipeline create info knows it, and the layout will have it as a part of it. So Vulkan will be looking forward to having the descriptor. Similarly, once that is done, we create the camera here, and now we need to create the descriptor pool. So descriptors. Okay. What is a descriptor pool? So each descriptor set is effectively a set of handles to some resources. These handles themselves need memory, and this memory comes from a descriptor pool. So we can create descriptor pool, which takes a device, no problem there. Descriptor pool, create info, null pointer on the allocation callbacks, and descriptor pool here, right? This is VK check. All right. So VK descriptor pool create info, first to explore pool create info. Okay. Structure type descriptor pool create info. P next is null pointer. Flags is 0. Max set. How many sets would we need? So for each frame that is in flight, we will need one set per frame. So we make it 3 because we're using 3 frames. But we can actually query that. So get num frames right there. Pool size count. How many pool size are we giving? One single pool size. And that will be a pool size here. Okay. So what is pool size? VK pool size. Or it's the expression again, pool size. Type is uniform buffer and descriptor count is 3. It's not 3. It's actually render device dot get num frames, right? So as many descriptors as we need. So we have 3 uniform buffers. 3 descriptors of uniform buffers, okay? And those can be created in the pool where we can have 3 sets total allocated. So each set will get 1 uniform buffer based on this particular thing. All right. And this uniform buffer itself, we need to have 3 of them, which can be a little bit of a pain. So we won't do that. Instead, what we will do is we will multiply the size by 3. Just have a single buffer of the size 3 times what it needs to be. Okay. That's it. You just keep 3 times the size that is required. And we'll get to it on how it works. But uniform buffer did. Is there a dynamic uniform buffer did? Buffer usage. I don't think so. So uniform buffer did. There's property visible. This is fine. All of this is okay. The only difference will be here. Uniform buffer dynamic. And we search for the other uniform buffer. We make this a dynamic variable. So dynamic uniform buffers allow us to just add an offset to the uniform buffer as we go. So you don't have to bother with, things. Tool create info. And now there's our symbol because it's called tool create info there. We'll replace it like this. Cool. So we have created descriptor pools. That is fine. Actually, we have constants with be with constant. I'll remove the dynamic parts. It's nice to have, but it's a lot more work for something that is not going to be used much after the initial parts of the code. And my GPU is fast enough that this particular race condition, which will be a race condition by the way, won't be a big deal anyway. So const. This can't be const expression because get num frames is not a const expression. Expression did not evaluate to constant. Again, this one probably is not a constant either. So it's a const expression, but it's not a static const expression. So it does, in fact, have an issue with it. But it's just fine. The solution. Okay. So far, so good. So descriptor pool was created, descriptor pool must be deleted. As it goes in Vulkan, everything that goes up must come back. Destroy descriptor pool. Takes the device, takes the descriptor pool, takes some callbacks which we don't have. The descriptor pool will be take that there, and we got the descriptor pool. What's next? Did we destroy descriptor set? We did. So after descriptor pool, we have to allocate the descriptor set. So vk allocate descriptor sets right there. Takes the device, takes allocate info. So descriptor set allocate info, and it takes the descriptor set. There's only one here, so something to take into account. Does it return something? Auto x equals. Yes, it does. So we can check. And we'll have to create a descriptor set. allocate info, const descriptor set allocate info, style vk structure, right? Descriptor allocate info. Emacs is null pointer. Descriptor tool is descriptor tool. There, descriptor set count is 1 and set layout is descriptor set layout. All right. So far, we have barely managed to create things. This descriptor set doesn't need to be destroyed because it's an allocate call here. It comes from the pool. And when the pool gets destroyed, this will automatically get destroyed and we don't have to work with it anymore. We do need to bind the uniform buffer to the descriptor set. So we're not done yet. We can write descriptor set. Okay. This is a structure. So write descriptor set dot doesn't initialization. So we can structure I write descriptor set. The next is null pointer descriptor set. Is descriptor set destination binding is 0. There's only one binding there. And element is also 0. Descriptor count will be 1. Descriptor type will be VK. Descriptor type uniform buffer. We just want uniform buffer, so I'll remove that. Image info is null pointer. Buffer info is something we will put in a second. So here we'll take buffer info. Okay. That needs us to create VK descriptor buffer info. Lot of work. Buffer is camera uniform buffer. Offset is 0. Range is size of camera data. Right? So that's it. Buffer info becomes descriptor buffer info. And there we go. Okay. Descriptor has been written to. We're done. Now, with that, we need to just do VK update descriptor sets. Device is device. Descriptor write count is 1. That is the write descriptor set. Copy count is 0. Copies is null pointer. It takes nothing. Luckily, this just works. Cool. With all of this, finally, that data that we wrote for the camera should now be inside the shader. Look, there is one problem. One more step that we missed. Here, after we bind the pipeline, at some point, we also need to bind the uniform buffer. Bind the descriptor set, I mean. So command buffer, so that's command. Pipeline bind point is VK pipeline bind point graphics. Layout is misc data. Layout, so it's pipeline layout. First set is 0. Descriptor set count is 1. Descriptor sets is misc dot descriptor set layout, not the layout, descriptor set itself. Yes. And dynamic offsets is 0. And it's null pointer for the dynamic offsets right there. This will write the code. I'm just going to reformat it. There we go. Okay. So it's just going to write the code into the system. And there we go. This is the triangle. It's the same triangle that we had before, but we're looking at it from a different position. We're looking at it from 1, 1, 1. Right? Actually, something seems to look a little wrong. No, it's fine. The triangle itself is an isosceles triangle. So that does look fine. I will shift it from an isosceles triangle to a quad. So this shader is no longer triangle. It's more of a mesh. .slang. Okay. Here I'll have to search for triangle .spv right there. It becomes mesh .spv. Build, build solution, compile everything again, right? Just run it and it should run the exact same thing. That's okay. Next, we don't have to modify anything. We just need to take the pipeline. I will rename this from triangle pipeline to mesh pipeline. Next, we'll rename it. Build again, see if it is building properly. It is building properly. Okay. We just need to go to the vertices. And we need to add 3 more. So, comma, and we add these. Now we need to independently allocate each of these, but first this needs to become 6. We're keeping this a static allocation, this whole thing. Nothing here is dynamically allocated. Okay, so position should be minus 1.0. So it's the bottom left corner. Okay, I will put a comment. So bottom left. Hold on. What is front face? So front face is counterclockwise. We need to remember this. Bottom left. So if we look at a triangle, something like this, we have one here. So this is top left, bottom left. We have top right. We have bottom right. Okay. We want to create a triangle that goes like that. Between these, it has to go like that. And we want some slashes, something like this. We will correct it soon. There we go. So 1, 2, 3, 4. Here's something like this, right? And we want to go counterclockwise, which means we want to go bottom left to bottom right to top left. And the second one will be bottom right to top left to top right. Here, what we can do is we can use, instead of using triangle list, so triangle list, we can use a triangle fan or a triangle strip. So we'll use strip. So now with triangle strip, we don't actually need to write this, like all of that. We just need to do that and it will pick it up. So bottom left, -1, 0. All of this is fine. Bottom right, so positive on the x-axis, still negative on the y-axis, and 0 on z-axis. This one will be, so we only need 4 now, which means we still need to correct this particular part inside vertexes. Yes, I could use a vector and it will crash, so I'm not going to use it. Bottom right. Oops. This one will be top left. This one will be top right. Okay, so top left. Left is -1.0 and top is positive 1.0. Z will be at 0. Similarly here, top right, so right is positive 1.0 on this and positive 1.0 on that. Build, run, Okay, that isn't correct. That is definitely not correct because it's only drawing a triangle. And the reason is drawing only one triangle is because here, when we say draw, we say the vertex count is 3, which again, it's not. So what we want to do here is we want to go into vertices and say dot size, static cast, of course. Build solution, run. That didn't work out. That didn't work out at all. Vertices dot size was 4. Why did it not work out? You can check triangle strip. Vulkan primitive topology, triangle strip. So what does triangle strip do? Connected triangle primitives. It's going to open the specification for that. With consecutive triangles as edges. So here, triangle strip says, if I say 0, 1, 2, and so that the winding order is consistent throughout. So 0, 1, 2, and then it will be 2, 1, 3. Okay. 0, 1, 2, and then 2, 1, 3. Is that okay for us? 0, 1, 0, 1, 2, and then 2, 1, 3. It is still anticlockwise. Yeah, it's not BRTL like that. It is TL, BR, TR. That is what a triangle strip does. Let's check the spec properly. Number of primitives generated is equal to 0. Vertex count minus 2. Expected. Primitive topology. Triangle strip is what we did. Okay, that seems to be not working for whatever reason. So what reason can it be? Build solution again, run it. So that's okay. Our colors are desynchronized, so I will synchronize it once. Bottom left corner will take 0, 0, 0. Okay. -1. So this becomes 0 and 1 becomes 1. Okay. Similarly, -1 becomes 0 and 1 becomes 1. Finally, 1 becomes 1 and 1 becomes 1. During all of this, blue will always be 0.5. Okay, build solution. What else can be the issue? Well, there it is. Vertex buffer size is size of vertex times this thing, which is not good. So what I'll change it to is vertices. Okay. It takes size of vertices, multiplied, vertices 0, sorry, and multiplied by size of, actually, it was just vertices by size. In reality, we don't even need this because size of vertices will be equal to this whole math. We can check this. So static assert this thing equals size of vertices. And it works, see? The only reason I'm keeping it separate is because in the event we change it to something like vector, this will still be correct when array will stop working. And that will silently stop working. Like array will silently stop working. Now, with that, it should be writing to the vertex buffer. There we go. We now see a side of like a square from a particular viewpoint. We can remove the 0.5. We can leave it in for the ones where everything else is 0. And we can remove it from all the other colors. That way the other colors get a chance to also shine. There we go, right? Things are working. Now, based on this, we can extend it to make a cube. A little bit of a pain to do it with the triangle strip. It is it because a strip can only go continuous sides. So one side, then a second one goes to the bottom. You have to make it in a very unique way. We are not going to get into it right now. We don't want to, bother with all of that. First, because we now bought the camera, let's also get to rotating things. So rotating things uses model matrices. Model matrices are a little, let's say, difficult to implement right now because we only have one thing. We don't want to add additional uniform buffers for all of that. So instead, I'll do a simple thing, which is model matrix gets added as a part of camera data. This is entirely and completely wrong. Okay? So beware. I warned you, it is wrong. Alt enter, create field, glm mat4 x4. Okay. And that should get its job done. Reformat the code. So with that, if I turn this on, things won't work because mesh.slang doesn't have it. So we'll put that here, float 4x4 model, and we put the model inside this. It will be here, camera.model, one more bracket. Now if we run this, things are same because I have only put an identity matrix at the model. Okay. This is an identity matrix right here. So what I will do next is change the model matrix on each frame inside blaze.cpp. So at the top of SDL iterate here, we wait for fences. So all the resources of this particular frame index are free. Once that happens, we will, update things. So now here I'll take the buffer. So misc dot camera data dot model matrix. Okay. GLN. So this is equal to GLN rotate matrix transform has to be included. So rotate. What does it take? First, it takes the matrix itself. So copy that, paste it there. Second, it takes an angle. So how much angle do I want to, rotate this by? Let's say 0.5, 0.1. We want it to be in degrees. So radians, let's make it 1 degree. So it will do 1 degree per frame. That might be a bit too fast. So 0.1 degree should be fine. SDL app iterate. And axis, which is nothing but vertical y-axis. So GLM vec 3, 0.0, 1.0, 2.0. Okay, now we'll keep rotating this model matrix. This is not enough because this is doing it on the CPU. We need to copy this to the GPU. So mem copy destination would be misc dot camera uniform buffer PTR, which we don't have right now, but I'll write it soon. Source, which is misc dot camera data. And size is size of misc dot camera data. Now, here's a little thing. I can actually write just the model matrix. And I can also here add offset of model matrix, which is probably what I will leave it to be. Do not find the symbol. We'll go to list data first. And after the uniform buffers, PTR, make this a U8 pointer. Oh, right. U int 8t. One of these days, you'll see this just disappear and you shouldn't care about it, right? So pointer, we model copying only the model matrix. We will move misc dot camera data dot model matrix. So this will be offset of camera data and model matrix. Okay. What's your problem, eh? Oof. We're gonna skip this. It's fine. Let's copy the whole camera data. It's not that big. Build solution. Done. Run this. Exception thrown. Writing location. Of course, since we never assigned to this. So uniform buffer. So here we get the allocation here. There's a map data. That's what we need. So men copy and then allocation info dot, not allocation info, sorry. We need camera data pointer is equal to allocation info dot map memory data. Okay. This means a cast. So dot interpret cast, and that works. Interpret uses a start type, so static cast. Done. Build solution, run it, and you can see it's doing its thing. It's going in a very weird way. And I am not entirely sure why it's doing that. That should not be happening. It is something weird. Okay, let's look at why it's doing that. Hold on. First, let's check if there are any errors. Doesn't seem like it is giving us any errors at the moment, at least. Axis is around 0. So axis is vertical. Camera target, that is the view matrix, which is fine. It's the model matrix, it says do nothing. Inside blaze.cpp, we are rotating it. So rotate camera data model matrix. Input matrix multiplied by this rotation matrix. Rotation angle. Well, rotation axis. Okay. So what is wrong? LLM max 4. If I am not wrong, it's just a matter of, nope, it is not a matter of that. Definitely won't work with equal to, but we'll see. Yeah, doesn't do anything. because it rotates this by a small amount and then never changes anything. So instead of pre-multiply, maybe it's a post-multiply. Nope, that's the exact same thing. So this was actually fine. List.camera data.model matrix. Something is wrong with something else. So model matrix is at 0, if I remember correctly, as in it's the identity matrix. But what I will do is I just go to the init ones, model matrix. Yeah, see, it initializes to the identity matrix. What identity? Okay, let's do a thing. Let's look at it from the top. So instead of looking at it from 2, 2, 2, we'll go to, let's go x. So z equals 2 minus 2, and everything else is the same. Everything else is 0. So we're looking at it from the front, and that's what's happening to it. It goes around and rotates. It is rotating or not? Yellow is on the right hand side. Yellow is on the left hand side. It is in fact rotating. It's rotating around the point which is not the point we want to rotate around. So why is that? What are our vertices? The z of the vertices is 0. They are x and y. So y is up, x is right. That's where they're set. That's where they are set. They can all translate. Let's do a thing. Let's make them non-translatable for a little bit. So when you use homogeneous coordinate system, the 1 or the 0 at the end helps you say whether something is, okay, that did not work out. Something is a direction or a position. Of course, it expects a position, so this wouldn't fly on this paper side. Did I do something wrong here? The model is the first one. Model is the first one in our code as well. We multiply by model, then view, then projection. That is correct. But this seems to go out to the edge of our view and edge of our view on the other side. If I move further away from, if the camera moves further away from this, does it change things? You see, it still goes all the way to the edge of the screen. That doesn't make sense. So this means that the entire rotation here is built on top of the view. Based on the view, the rotation's math is changing. Which means there is something wrong with my mathematics here altogether. Model matrix, view matrix, image projection matrix. Here, model view projection. Let's check the camera data. Model. Aha! There! It wasn't, in fact, in the right location. These kind of things are something you have to be careful with. You see, now it's working properly. These kind of things are something you have to be very careful with, because the only communication between the shader program and our CPU side program is the memory layout. So if the memory layouts are wrong, neither side knows what's happening. And because the problem was a little, let's say, just ordering changes, it did a weird thing with how it moved around. But that is fine. Now it seems to be working. Okay. let's see how many FPS this is giving. I think it should be around 60 FPS. It's doing 5.4 relaxed. 5.4 relaxed is a VSync method. VSync means we will get 60 frames per second or something. Whatever my CPU is running at, whatever my display is running at right now, I'm checking that 144 hertz. Okay, we can test this out. The way to do that would be, well, one of the ways would be to actually get SDL to print. SDL get frame time. SDL3 get frame time. Oof, so bright, so bright. Performance counter and performance frequency. It is only okay. So that is it. You see, it has this whole counter thing here that we need to move. Light, dark, light, dark. Such painful. Okay. So we need to get the SDL state and we need to keep the state intact between times. And again, we're going to use this miscellaneous data for everything for now. So you in 64 as the SDL version, but we'll just use the standard version. So you're in 64T, timestamp, but actually it's more previous query. Interesting. How do you spell previous? That's how you spell previous. Previous counter. That's it. That's all we need. So inside init, we will say previous counter equals 0. And inside the delta iterate, so you will 64T previous and counter equals misc dot previous counter, then previous counter on the misc side, you will 64T current counter equals SDL get counter. That gives us a current counter. So previous counter minus current counter, previous counter minus current counter. And hold on. This will be inaccurate because we're waiting for fences here. This will be more accurate because this will actually block our CPU. Okay. Previous counter minus current counter, that is wrong. Current counter minus previous counter is the more accurate one. You will 64 T delta count. What's that? We don't actually need to do this like this. All of this becomes static cast into a double. Okay, we're going to use double precision time for now. Make it float. Make it float. So float precision time and divide by SDL, get performance frequency. Okay, that gives us delta time, and this will be a double. So float. So float delta time. Okay. Now previous counter and current counter are done. We will say misc dot previous counter equals current counter. SDL get frequency gives us a event 64T as well. What's your problem? Narrowing conversion. Bug throw. Hey, let's make it double then. Just still a problem with you? It seems to be still a problem with you. Double, and that's it. Not clear. Over here, and with that, loses floating point, so we'll choose that with a boolean. Okay, so far so good. Then we get const, so we do it. We get const here. State can be const, probably. Yes, it can be const. We don't care. So delta time, and inside rotation, we can say this is one rotation per second. So that's delta time right there. 1 degree per second, sorry. For reflecting template parameters. What a mess. Float here, I'll float there. There's a possibility this actually, hold on. So if there are too many significant digits in the unit, in the performance query counter, that will lead to a loss of precision when we do the floating point. So instead, we will cast it with double manually and then do a conversion here. So that should be fine now. Delta time is const. Build. Okay, run. That's 1 degree per second. And we should show this on the screen. So str set title window is app state window. Title is str s printf. Here's printf. We need a buffer here. Can create a buffer of characters. So char buff of I don't know, almost 1,000 characters, let's say. Make it a global, make it like we didn't care. So gbuff character like that. And we'll take that buffer here. So gbuff constant format, which is percent %f. And it takes the delta time. That is delta time. It also takes previous counter and current counter like that. So it gives f percent LU. Okay, that is done. Title, this is gbuff. And we remove both of these down here. So they don't affect the calculations anymore. Yes, printf has 3, but it's called with 5. It's a VAR glitch. What are you talking about? Ugh. Hey, dot F only. This is okay. VS printf VA list. Said not how you do it. See VA list. How do you create it? Deprecated is unsafe. Should use vsprintfs. Fine, we'll use vsprintfs. What do you need now? So you take a size parameter here. So we'll take from 1,000. Okay. The list is printfs. Value returned by this function should be used. Auto equals. We don't actually need to use it. Clearly, VA list is not called that way. CPP help to create a VA list. Complete object in a particle you need built-in type of cluster for storing. Create a VA list. Use. That is definitely not what I want to do. Arts. Okay. Let a pain. Sprintf. Sprintfs. That's the one I needed, not the other one. Previous counter. Current counter. Okay. Instead of logging all of this, we can just make the window title this. That allows us to see what we're doing quite nicely. So 0.006. This is being very shaky. It's trying to increment. Delta time is fine. Okay. Something is clearly wrong. How delta time is increasing, changing our rotation. So if you go to the rotations here, radians is 1 degree times delta time. We can just say it's 60 degrees times delta time. Okay. Now run it. That's smooth. It's 0.069. That doesn't tell us FPS. That is just what it is. So we switch it to FPS, which is not the right way of doing things, really. FPS shouldn't be used. But, gamers be gamers. FPS be FPS. So, we only do 4 precision points or 5. Well, this gives us seconds. So for MS, we will multiply this by 1000. For D, that would be this thing. So I'll actually say auto delta time MS equals that, and auto FPS equals 1.0 by delta time MS. Okay, double and double. Cool. So now I can just say FPS and delta time MS. Those are massive numbers. Also, those are incorrect numbers because we asked for a decimal point when we're providing it floating points. So now we'll do 0.2. I don't think we need to go more than 2 decimal points in FPSs. 0.14 FPS. Excuse me? 6 milliseconds. That can't be 0.4 FPS. That makes no sense. Oh yeah. It's 0.4 frames per millisecond. 143 FPS. That makes a lot more sense because my screen is 144 hertz. So that's the rendering speed I'm getting. All right. So we've got a square, it's rotating. That's it for today. Tomorrow we will get into actually changing from rotating squares to getting textured squares into the system. So we'll add textures into it. And we'll do a little bit of cleanup so we don't have that misc data have everything in it. So hope you all enjoyed. Have fun. Have a good night or good day, depending on where you are. It's 5 p.m. somewhere. See ya. And thanks for watching.